Okay, so today we start our first real lecture in this quantum computing part, and the first thing that we will consider today is the transistor of the second quantum revolution, which is qubit. Okay, but before we do that, we will consider two quantum models. Like always, when we deal with real life, stuff is complicated. But when we want to understand it, we usually simplify it, classify it to something simpler. So when we are talking about quantum physics, there are two rather simple models, but which many real systems fall into one or two categories, in one or another category, depending on the structure and how we use them. So one category is the two-level system, or qubits. So this is a system in which we have just two states. For example, ground state, G, excited state. So just two discrete energy levels or two discrete quantum states. Another very simple but very useful model is the model of quantum harmonic oscillator. Well, you all studied quantum harmonic oscillator in introductory courses on quantum physics. You know that if we have a particle in a parabolic potential, there will be discrete energy levels, but there will be infinitely many of them, and the energy distance between neighboring levels is always the same, and we can write it as h bar omega, where omega is exactly the same as frequency of the classical harmonic oscillator with the same parameter. So this model is also very useful. So here we have this infinite ladder of equidistant levels. And it applies not just to harmonic oscillator. It applies basically to everything when we have oscillations of waves. For example, if we consider electromagnetic field inside the cavity, there is some resonant mode. And this resonant mode, using proper mathematical analysis, can be mapped exactly to the quantum harmonic oscillator. And therefore, this is like the first thing studied in quantum optics. So also in quantum optics, we don't have oscillators itself, but mathematics is exactly the same. It also applies not just to oscillations, but to propagating waves. If we consider, say, electromagnetic wave that has a particular wave, electromagnetic wave in free space, that has particular wavelengths of a vector, it will be mathematically described exactly by this model. And this energy level, this number, basically corresponds to number of photons in this particular mode. Okay, so this two-level system of qubits, they are very good for encoding digital information, because here we have clear two states, and we can say, okay, this state is 0. If system is in this state, we have digital 0, and here we have digital 1, and nothing else. So this is very good for encoding digital information. Okay, and of course we can have superposition, because this is quantum physics. This is something that we will consider in a moment. Quantum harmonic oscillators are not so good for encoding digital information. Why? Because I can say, okay, this level corresponds to 0, this level corresponds to 1. And I would say I will not excite all other levels. But this is very difficult to do. Why? Because how do we move system from level 0 to level 1? Well, there is a frequency energy difference h omega. So we shine a light, or we apply this portion of energy h bar omega to move from this level, from 0th level to the first level. But if it happens that the system at that time when we apply this energy is in state 1, or there is some part of superposition which corresponds to state 1, well, the system will absorb this amount of energy and move to state 2, to state 3, and so on. So we cannot localize, it's very difficult to localize the system just within these two levels in quantum harmonic oscillators. The reason is that because this energy step is exactly the same between each two levels. We can still use it as some encoding of information, but we have to be really careful, and generally it is much much more difficult. Here it's simple. If we have just two energy levels, whatever we do, we will have 0 or 1 or some quantum superposition of it. Here we have to be careful. But such systems, such quantum harmonic oscillators, or more precisely like electromagnetic fields or some other fields, they are used to control qubits, to control two-level system. So when we look at, say, current quantum computer from IBM, we have qubits, two-level system, but we have a lot of microwave resonators which are used to control behavior of qubit, to do some operations on qubits, and to read the state of the qubits. So this is like our digital quantum bit, qubit, and this is actually machinery how we do stuff with qubits. So interesting things happen when we have both of this system and they interact with each other. But for now we will focus more on this, on the qubit state. So there are only a few examples in which we can say that, okay, this is a system that has exactly two levels. One example is spin 1/2 particle, like electron spin. So electron has spin 1/2. That means that there are two discrete levels, spin up and spin down. If we have magnetic fields, their energies are different. If there is no magnetic field, their energy will be the same. They are degenerate. But there are only two possibilities for spin 1/2. So this is one example. Another example of system with two discrete levels is the polarization of photon. When photon propagates, electric field must oscillate perpendicular to the direction of polarization. So for photon propagating in this direction, electric field can oscillate either in horizontal plane, so this is horizontal polarization, or in vertical plane, vertical polarization. And usually when we are talking about photons, these energy levels are degenerate, meaning that, well, we have the same energy for one state and for another state. Okay. So there are just two of such examples that we can say, really, this is a system that has only two levels and that's all. But but real multi-level systems that has many energy levels, many quantum states, sometimes can be considered as two-level system if this energy separation between levels is different. For example, here I show schematically, well, typical spectrum of an atom. When we consider atoms, there are energy levels. So these energy levels, like one energy level, second energy levels. So these energy levels, they correspond to electronic excitations. So this energy levels, so when you studied hydrogen atoms, you had only energy levels like that. But this is not the whole picture, because this energy, usually we have splitting of these energy levels because of some additional interactions which are not taken into account in the simple hydrogen model. For example, hyperfine interaction, a less interaction between spin and orbital motion of electron and so on. So these energy levels, which were just like one state in a simple model, they often split. But this splitting typically, because these are weak interactions, like hyperfine, so you can understand that this is very weak interaction. So this weak interaction leads to only to very small splitting between energy levels. So if we have a structure of spectrum like this, we have hyperfine splitting. This hyperfine splitting will be like frequencies that correspond to this transition will be like order of gigahertz. Here we have electronic transitions. So this frequency is terahertz or 100 of terahertz, like optical photons. So there is a huge difference of energies between these two levels and this. And if we operate if we use such atom, we can send, say, signals that correspond only to transition between these two levels. And such atom will never go into higher atom. A higher energy state. So in that case, we can use such atoms as qubits. And this is what is actually done. There are several companies are using atoms, either neutral or ions, as qubits, because they use this large separation of energy. They can isolate two levels which we use to encode information. These higher levels, they are not completely useless. That can be used to manipulate qubits. For example, we can choose these two levels such that the direct transition between them is prohibited. A photon cannot be, like if atom is in this state, it cannot emit photon like using, say, dipolar mechanism to go to the ground state. That means that this is actually good because it means that qubit will live for a long time if direct transition is prohibited. Then how we can move atom from one state to another here? Well, we can excite atom there and then induce transition to another level. So that's possible. So this higher order levels, they are useful because they allow us to manipulate qubit. We can also use this higher energy levels to read state of the qubit and so on. So this is one example how multi-level system can be treated as a qubit and when it behaves as a qubit. Another example is that when we start from quantum harmonic oscillator, we have this nice equidistance ladder of energy levels only in the case when potential is exact parabola. So in language of classical physics, that corresponds to the case of linear oscillator. So restoring force is proportional to displacement. So you have mass spring system with ideal springs that satisfy Hooke's law for all extensions. So this is the case of linear or harmonic oscillator, as name implies. But if potential is not exactly parabolic, if it is has some different shape, which physically in a classical language corresponds to nonlinearity. So we have a spring that becomes more stiff as we extend it, or less stiff that we extend. So potential is not exactly parabola. So then the energy, we will still have this ladder of energy levels, but energy levels between different, energy separation between different levels will be different. So here we have one transition frequency, here we have different transition frequency, and so on. In that case, again, we can use such system as a qubit if we are careful and we ensure that of everything we do with qubit, well, for all our operation, qubits will not leave these two states. And in this case, for anharmonic oscillators, this is possible. And actually, superconducting qubits, they are exactly this type of qubits. So what is superconducting qubit? Superconducting qubits is just LC circuit. We have inductance, we have capacitance. So this LC circuit is oscillating system. If we have real LC circuit like here with all linear elements of usual inductance or usual capacitance, we have exactly parabolic potential and equidistance energy levels. So what do we need to do for with LC circuit to turn it into a qubit? We need to introduce nonlinearity. And nonlinearity is introduced by Josephson junctions. So here we introduced, instead of usual linear inductance, we introduce Josephson junctions, and they have strong nonlinearity because current through Josephson junction, it depends on sign of phase difference on two sides of Josephson junction. And sign is a very nonlinear function. So if you do the math, you can calculate like effective energy potential, and it will have form of cosine function. So now we have strongly anharmonic oscillator, and energy levels are not equidistant, and we use it as a qubit. So this is how superconducting qubits. There is nothing more than just nonlinear LC circuit, that's all. Okay, and we use two lowest levels to encode information, and we try to always keep qubit in these two levels, but higher order levels can be used to read the qubit state, to perform some manipulations, and so on. So they're also useful, but important. Okay, So now, where are magnons in this classification? So we are talking about two simple models. Qubit, quantum harmonic oscillator. So where are magnons? Here or there?
We can couple magnon to this superconductor.
Well, we can couple, look, if you have qubit, you can couple it to this. If you have a quantum harmonic oscillator, you can couple it to another quantum harmonic oscillator. If you have qubit, you can couple qubit to another qubit. So these systems, they can be coupled as one. But if we are talking about magnons, so what would be the proper model to use? Is it qubit or is it quantum harmonic oscillator? Yes?
That's the quantum harmonic oscillator.
Why? Like we are talking about spin waves, and spin is spin 1/2, so we can flip it only once. So there are only two energy levels, two states for a spin. So why are you saying that it's this?
Because they're bosons.
But spin has only two levels.
But not in a, for one magnon, it would be one spin, and a magnon is a collective excitation.
Yes, this is right. This is very good answer. So there is a big distinction between individual spin and magnon. So individual spin says here, this is a very nice model of a qubit. But magnon is a collective excitation. We have many, like 10 to the order of 18 spins. If we flip one spin in this array, well, if we flip it properly, as I showed on the last public lecture, well, we will go to this state, we will have one magnon. But we can flip two spins, one here, one there. We will go to this and to that. Magnons are not exactly bosons because we have finite number of spin, 10 to 18. So we have only like 10 to power of 18 energy levels, and that's all. But this number is so huge that we really never reach it. So magnons sit here, individual spins sit here. Yes?
How about if I will make very small sample, one lattice constant, will I switch to single spin?
That's a very good question. And what will happen is that it will not, if you increase, so as I said, we have finite number of spins, so this is not exactly quantum harmonic oscillator. What it means on this diagram, that this distance between these energy levels is not exactly the same. So there is some nonlinearity, and we know from classical physics that classical magnons have nonlinear properties, they have nonlinearity. So if you consider this energy levels, this energy separation will not be all be the same, there will be some small. If we consider spin, like macroscopic sample, like X sphere of 100 micron diameter, then this like unharmonicity, difference of energies between 0, 1 and 1, 2 transitions, this is what we are interested in, will be extremely small. But when you scale down size of ferromagnetic materials, you increase this unharmonicity, and then you get basically to this picture, and then you can use magnon as qubit without any additional precautions. And there is research in that. Basically, the question is how. Okay, natural nonlinearity of magnons in macroscopic samples is not enough to provide the separation in energies. But there are research and there are some ways how we can amplify this nonlinearity, and this all goes under the term magnon blockade. So magnon blockade means that, well, if we excite one magnon, that this one magnon prevents second magnon to be excited like at the same frequency. It actually means that this separation between levels become different. So yes, and this is actually would be very interesting. And I think, I don't remember exactly, but I think some of homework problems ask about this. At what size of ferromagnetic sample you would get enough nonlinearity to be able to use magnon as qubit? Okay, so as I already said, that like these two models, it's not like one is better than another. And the most interesting thing happens when we have both of them and when they interact. So we use qubits to encode information, but to manipulate them, like on backend, how we actually manipulate this stuff, we need to use quantum harmonic oscillator. Well, when I talk we need to use quantum harmonic oscillator, what in reality we do, we use electromagnetic field. We have qubit, we send electromagnetic wave on it. And this electromagnetic wave does something with qubit. In quantum magnonics, we would like to see, instead of electromagnetic wave, we would like to send magnon and perform some operations on qubits. That also would be very interesting. Okay, so this quantum harmonic oscillators, they are backbone of old quantum gates that we do with qubits. Okay, but also qubits are important for quantum harmonic oscillators because, like, if we have just an electromagnetic field, there are not a lot of interesting non-classical states that we can create. Okay, we have lasers that create a particular state of light. Or we have like usual thermal sources. So these are different states, but they are both like very close, closest to classical state. What if we want to create some entangled state of light, or some one photon or one magnon state? How would you do that? And the way to do it is to use interaction between, say, electromagnetic mode in a resonator and qubit. And we can manipulate this interaction in such a way that it will create some non-classical state of our system. And this was also done with magnons, and one of research papers in this recommended list of papers describes exactly this operation. There is interaction of magnons in X-sphere with qubit, and this interaction is used to create states of magnons which are not possible to create otherwise. So these two models are interdependent, I would say so. But in the first part, we will focus mostly on qubits, and we will not consider in too much details of how actually to manipulate, like what is the engineering and what is the exact mathematics of manipulating these qubits. We will use just some simple models and some simple assumptions and so on. So because if you write a program and you write like you type 2 + 2 equals and computer tells you 4, it really doesn't matter for you how this answer was achieved. So this engineering is not that important if you want to understand what is possible to do, say, with mathematical operations. So here we will consider what's possible to do with qubits without looking too much into engineering side, because anyway, engineering side changes very much. We will cover it just a little bit, and more about engineering will be covered in the second part of the course. Okay, and we said, so let us look at this qubit. So qubit has two levels, two states. So these are two basis states, because as you know, with quantum system, we have superposition. And if we have two states, we can have different superpositions of these two states. So total number of states is infinite. But there are two discrete basis states. So we can write any possible state of qubit as superposition of these two states. So this is a difference when we are talking about states in quantum physics. So what does it mean that it's two-state system or three-state system? It means that we have two basis states or three basis states. And all other states can be obtained as a superposition of this. Okay, now physical meaning of this two states different and depends on type of qubit. Not just physical meaning, but like standard notations for that. For example, when we are talking about photon and polarization of photons, so there is horizontal polarization and vertical polarization. So we denote horizontal polarization usually as CAD vector H and vertical polarization as CAD vector V. So, and it has meaning of different polarization. For spins, well, we have spin up and spin down. So spin up and spin down. When we are talking about atoms, well, we have ground state, which is usually denoted as G, and excited state, which is usually denoted as E. So there are many different notations, but when we are talking, when we are talking about, say, quantum computing, it is not convenient to use this different notation. So what we do in quantum computing, we always denote one state 0 and one state 1. Okay, so one note here. So in most qubit realizations, these two states have different energies. They are physically non-equivalent. For example, suppose we have atom with such structure. If atom is here, it can spontaneously radiate photon and go to the lowest level. So there is possibility of spontaneous transition from this excited state to ground state. But inverse process is not possible if there is no like thermal noise and no other noise. So they are physically non-equivalent, usually this state. Okay, but they are exactly equivalent from point of view of information state. So this is 0 and this is 1. So there is no difference between them. Like you can apply NOT operation and to turn ones to zeros and zeros to ones and switch their role. Okay, so physical nature of of this basis state. It is not important when we want to understand what can we do with quantum information, what can we do with qubit. It's the same as it's like if you analyze what you can do with your laptop, it's absolutely not important whether logical 0 corresponds to high voltage or low voltage. You probably don't know this here. So physically, the 0 and 1s inside your processor, they are different. But it absolutely does matter when you write a program or you want to understand what is possible and what is not. So this is important only when we want to analyze how we can do one thing or another. Like if you want to create XOR gate in your classical computer, you need to know whether ones are high voltage or low voltage. So for now, as I said, we are not going too much into technology, so we want to analyze what we can do with qubit, and we will treat this state 0 and 1 as completely equivalent, regardless of the fact that they usually have different energy. We'll see on the next lecture that this is not big of a problem, that we actually do the same in our everyday life without thinking. Okay, so like this. So we will treat the 0 and 1 as completely equivalent state. Yes?
When we measure our system, we know that it's a very basic question. When we measure our system, we know it is in the ground state or in the excited state. How do we know the system lives in superposition state without measuring?
That's a very good question. Let's wait till we will go to the measurement part of this lecture, okay, and then we will discuss it. Okay, that's very good, very deep question. Okay, and last part of this lecture is about measurement, so we will discuss it there. Okay, so we will treat this state 0 and 1 as completely equivalent. So you can create like visual picture of two photon polarization, which are exactly the same, or you can think of two direction of spins if there is no magnetic field. If there is no magnetic field, there is no difference between up and down, right? Or between left and right. Okay, so in quantum computing, these two states, they are denoted 0 and 1, regardless of realization. So we can talk about qubits, and everything we will do, we will talks that we can do with these qubits, you can realize with superconducting qubit during your labs. You can use some other quantum computers that do the state with qubit based on atoms, or you can run simulations. It doesn't matter what is the realization, it's always 0 and 1. And these states are called computational basis states. Basis, why basis states? Because we can form superposition between them, and also basis here has a very exact mathematical meaning. So what is a basis in classical physics? Like, what is basis? Basis is a coordinate system. Coordinate system in classical physics, what it represents? It represents 3 orbs which are mutually orthogonal. They have unit lengths and they are perpendicular to each other. So you can use any coordinate system you want, but you need to have 3 orbs, unit lengths orbs, mutually perpendicular. That's your basis in classical physics, that you use every time you solve a physics problem. First step is to use coordinate system. So these states also form a basis. So they have unit lengths, so they are normalized. Are you familiar with this notation? Good. Okay. So their scalar product equals 1. Scalar product of vector is itself is length of the vector squared. Okay. So they are normalized. Normalized means like this condition of normalization written in such compact form is the same as if you write that integral of wave function squared over all space equals 1. Like probability that we have a particle anywhere is 1. So these states are normalized and they are orthogonal. So scalar product between them is equal 0. So this is the same meaning as triple of orthogonal vectors in real space. Okay, but these are just basis states, and in quantum physics, we have principle of superposition. So if we can have system in state A, or system can be in state B, it can also be in superposition state like that. So we have, for qubit, we have systems that can be state 0 or in state 1, so we can form superposition of these 2 states like this. Okay. And here is this number C0 and C1. They are complex numbers because in physics we need to have complex numbers, but we actually can explain why do we need complex number using simple example. Suppose this is a light beam, and I can demonstrate oscillations of polarization simply by oscillating it. So this is horizontal polarization of light. This is vertical polarization. I can form superposition of both horizontal and vertical motion. It's like that. So if I use here like diagonal direction, that will be horizontal plus vertical. If I use diagonal in different directions, this will be horizontal minus vertical, right? How do I mathematically describe motion like this? It's also superposition of these 2 oscillations, because this 2-dimensional pendulum does not know how to move in any other direction. So this is superposition of horizontal and vertical polarizations. What's the difference from this superposition? The difference is that like when I have superposition like this, both my horizontal and vertical component change in phase. Cosine omega t for horizontal and cosine omega t for vertical. If I have circular polarization, one component changes as cosine omega t, another changes as sine omega t, because we are moving along a cycle. So one coordinate is cosine, another is sine. So there is phase difference because sine is just cosine plus 90 degrees. So there is a phase difference between this horizontal and vertical polarization. And how do we describe phase difference? We describe it with complex factors, e to the power of I times phase. So this example shows that we really need complex numbers to describe superposition of states. So it's not something that, well, you can get it mathematically, but you can get it from very simple consideration. Okay, so these two numbers are complex. And now this state, to represent a physical state, we still have normalization condition. Length of this state should be equal to 1. So scalar product of state with itself must be equal to 1. Or in terms of this coefficient C0 and C1, we have C0 modulus squared plus C1 modulus squared equals to 1. So sum of all this coefficient absolute value modulus squared must be equal to 1. Okay, so here in this formula I use two different representations for the same thing. So this is Dirac form because I am using Dirac notations for 0 and 1, so these cat vectors. And this Dirac form is often very convenient when we analyze what's going on and we want to do it by hand analytically. So here I can represent the same vector in a matrix form or column vector. So this is column vector, but column vector is a part of matrix notations. So here is the C0 with the coefficient near 0. So I just like by convention, here is the place of 0, and here is the place of 1. So this state can be described by such vector forms. So vector forms are not that useful when you do calculations by hand. It is probably more like you used to use matrix notations because they are used in many different fields. This is one of the basic techniques. But very often when you want to analyze something, say analyze quantum programs, stuff like that, this form is more convenient than that one. Because this form is very useful when you do analytics or you're using computers. So computers think in matrices. Okay, so this is the general, most general form of a single qubit. This superposition with two complex numbers subject to this normalization. There is one very important thing about quantum states, and this is global phase. So you probably heard that global phase of a wave function cannot be measured. So if we have wave function psi, so this is state of some system, and the same state with different phi phase, we cannot measure this phase. And it's not just, it's actually not very good term that we cannot measure, because if I say we cannot measure it, I kind of imply that it exists, but we just don't know how to measure it, right? But we don't have any reason to believe that this global phase exists in reality. So it's just our mathematics. Well, we use complex numbers. We can put here global phase. We have zero experimental evidence that this phase is real. So mathematically, this is like a different state. But this is, we don't know if our mathematics is right, and probably it is wrong, because there is no experiment at all, and well, based on our theory, this is not possible at all. So this phase is not that it cannot be measured, it's unphysical, it doesn't exist. It's just the fact that we are using particular mathematical apparatus, that our mathematics is not 100% suitable to nature. And because of that, we have to introduce a normalization condition. If we use some proper mathematics, this condition would be satisfied automatically. If we use proper mathematics, we would not have two different states that represent the same physical state. Okay, but well, we don't have any other apparatus except complex numbers. So these two states, they physically represent the same state. Mathematically, yes, like if you run some numerics in your computer, you will get result like this, but I will get result like that, and I will check your homework, you will get F because they are different, right? But physically, it's the same. So we can denote it like with this. They are the same up to a global phase. So when you write quantum program, you write a quantum program, you create some gates and so on, and then you send this quantum program to quantum computer. And before running on a real quantum computer, this program has to be compiled into this machine codes which are understandable by a particular quantum computer. For quantum programs, this compilation is called, like for IBM quantum computers, it is called transpiling. Transpiling program from your code, generic code, into system of machine code understandable by computers. When you do it, very often, your global phase produced by your code will be different. And quantum computers never pay attention to that. Okay, we will have everything the same except global phase. Fine, it's the same physical result. So global phase is unphysical. Okay, so what is physical is a relative phase and what can be measured. For example, if we have here this general qubit state, general superposition. So this phase factor, it multiplies everything. It multiplies the whole wave function, whole superposition. This is global phase. You can put whatever you want there, you can drop it, it's unphysical. This phase, this is relative phase. So this is the phase between these two components of superposition. So this one is relative. This one can be measured, and we can measure it. So, and it has influence of states with different relative phase. It means they are different phase, because states with different phase is this. This is 0 plus 1, and this is 0 plus I1. They differ only by phase, and this is 0 minus 1. Again, just a different phase. Different relative phases correspond to different physical states. Okay. Okay, so if you ever drop phase, just be sure that you drop only the global phase. Yes?
Sorry, please correct me if I'm right. This is because of this relative phase we show the qubits in a sphere, instead of a circle.
Yeah. Yeah, exactly. We will go after this, we will derive the sphere. Okay, we will look at it. Okay, but this global phase has important consequence in quantum magnonics. So I would say there is one important misconception in quantum magnonics related to global phase. So let us think about single magnon and phase of a single magnon. Suppose that somehow we were able to excite exactly one magnon at the initial moment of time. So initial state of our system is just one magnon, and that's all. Single magnon state. How the state would evolve in time? Well, single magnon has certain frequency, omega, has certain energy, h bar omega. So we know that this state the phase of this state will change in time as omega t. So with time, we will have state which is like this. It just oscillates with magnon frequency omega. But when you look at this is global phase. This is phase. This phase factor multiplies the whole wave function we have. So single magnon does not have a definite phase. It's a very simple calculation and very counterintuitive result because you are using classical thinking. You're thinking of magnon as very small spin wave.
But I think that one, it's not the amplitude of
It's a state.
changes. It's a state. So
It's a state. It's the same state as I showed on a previous lecture. So there is down, up, 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 down, up, 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 down, up, 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 up. So it's a huge superposition, just shorthand notation for this huge superposition. But this is eigenstate of magnetic system. So this is a state with particular energy, h bar omega. So with time, it changes simply by changing its phase.
why did you multiply this on iomega t?
Because we have time-dependent Schrödinger equation. So here is our Schrödinger equation. Right? And now for single magnon state, so if we have state like this is Hamiltonian. So this is single magnon state. This is a state with a particular energy of one magnon. So we have this energy of one magnons, and it is eigenstate. Okay. So here I will write psi as some c as a function of time times this state, because I have one magnon. So I substitute it here. What I will have? I h bar, then I have derivative of this c. State 1, well, it's just a state, it doesn't depend on time. And here I have h bar x on this. So I will have this h omega c as a function of t1, right? Then this cancels, I multiply by minus I both sides. So I and minus I gives me plus. So what do I have? dc by dt equals minus I omega c. So from this c is e to minus I omega t. This is the same, like the only thing that we actually use here is the fact that it is eigenstate. That we have this. So if you have eigenstate with some energy, h bar omega, that would be the same result. So for example, if instead of one magnon, we created two magnons, so we have state 2. Two magnons have 2 times higher energy. So here I would have 2 omega, because this omega is just energy divided by h bar. Okay, so here we have, so if we have single magnon state,
Sorry.
what changes? It's its global phase with time, and we cannot measure it. Yes?
This complex number acts as an operator.
No, this is just number. There is no operators here. Operators is like, no, it's just a number. It's just a coefficient. So it's like here. These are CAD vectors. These are just numbers. And there is no operator so far except for Hamiltonian.
But when we have psi 0 ground state, we need
Psi 0 is not ground state. It's initial state.
initial state.
Yeah.
We need a unitary operator to get psi t.
Instead of doing all this, I can take this equation, I can get this equation, and I can solve it formally. Okay, so this is time derivative equals something. So this is operator. I can forget that this is operator. I can write solution as exponent of what I have here divided by this times time and what I had at initial moment of time. Write this. So this is what would you do like at higher mathematical level. Here I have operator, an exponent of operator. So this is another operator, which is we call it evolution operator. I just solve it like in first class. Okay, so here we have this operator. Implicitly we have operator, but we are talking about creating eigenstate of the system. So operator is just a number. Because this is you are right, that here I have operator that acts on this state, but this is eigenstate of this operator. So this is just a number. Okay, so this is what we have. If we have single magnon, what changes in time is its global phase, and we cannot measure it. So single magnon does not have phase. This is exactly the same conclusion as with quantum harmonic oscillators. If you remember, when you studied quantum harmonic oscillators in introductory physics, this is a potential, these are functions, eigenfunctions that correspond to zero state, like vacuum state, first state, and so on. This is a probability distribution. Does it change in time? No, it does not change in time. When we are talking about phase of something oscillates, we need to have change in time. Otherwise, what's the meaning of the phase? So single magnon state does not have a phase. How can we get a phase when we can talk about phase? Well, the only physical phase in quantum physics is the relative phase. Phase between different components of superposition. So to have, when we are talking about magnon, to have something like a magnon phase, we need to create superposition. For example, consider that the initial state of our magnonic system is like this, like half magnon. This is wrong term, don't use it. So it's a superposition of vacuum state and state with one magnon. So we kind of excited one magnon, but didn't finish the job. Stop midway. So how this state will evolve in time? Well, quantum physics is linear, so we know that, well, if we have state with a particular energy, it changes with time like this, where omega is this corresponding, is energy divided by h bar. So phase of this term will change exactly in the same way as in previous example. Quantum physics is linear. So we will have here e to I o minus I omega t. Here is the vacuum state. We will take zero energy there at the vacuum state. So this phase does not change. So this is what we will have. Here we have phase changes with frequency of one magnon. Here phase does not change. Now, look now at this phase. Now it is relative phase. It's not the phase of the overall wave function. It's a phase that defines relation between different components in superposition. And this phase can be measured. What we see as the phase of spin waves in classical physics is exactly phase like this. It's just states that we work in classical physics. They are so-called coherent state. They are superposition not just of 0 and 1, but we have 0, 1, 2, 3, and so on. And this component changed like this, rotates at frequency omega, 2 magnon changes at frequency 2 omega, and so on. And we measure this relative phase between these components. This is what we see as a phase of magnon in classical physics, or a phase of spin waves. Yes?
Half magnons means
well, it's a bad term.
The expectation value of our system is half, or
Well, yeah, like if you take like energy, expectation value of energy, you'll get 1/2 of h omega. But this is not a real term, so don't use it. I will remove it. It's confusing actually. Yes?
I have a silly question. Why this normalization factor is square root of 2?
Why? Because we need the total length of this state to be 1. So let's do this exercise a little bit. So what we need psi to be equal to 1. And say I have psi, which is some normalization factor, 0 plus 1, right? So here I have psi, so this should be bra vector times ket vector. How do we calculate bra vector from this? We change all ket vectors to bra and we complex conjugate everything that we have here. So alpha will be complex conjugated. So here instead of ket vectors we will have bra vectors. So we change this angle, direction of angular bracket. Okay, and here I have ket vector. So this is the same. So I have alpha 0 plus 1, right? Okay, I have alpha conjugated times alpha. So this is absolute value alpha squared. Then I have this combination. So when we work with bra and ket vector, we just treat them like matrices. So we can multiply, open parentheses, whatever. What's important is that order stays the same. So here I have 0, 0, 0, 1. Here is 1 plus 0, 1, 1, 0. And finally 1, 1. Like this, 4 terms. Now, these 0 and 1s, they may represent different things. Magnons, ground and excited states of electron, it doesn't matter. What's important, they form a basis. So form a basis, it means this scalar product of state with itself 1. And here is 1. And they are orthogonal. So this is 0. So together I get 1 plus 1, 2 alpha squared. 2 alpha squared, and it must be equal to 1. So from this I can choose alpha 1 over square root of 2. I can multiply it by phase. But this phase will be global phase. So it doesn't matter. Okay, so let's move on. Let's move on. So there is one important concept in qubit, which is Bloch sphere. So general qubit state has this form. We have C0, C1, and modulus squared of this coefficient must be equal to 1. Okay. So this allows us to rewrite this state in a slightly different form. So first of all, there is one important relation. There's one of 2 trigonometric relations that you should understand, that cosine squared plus sine squared equals to 1. So here I have a squared plus b squared equals 1. That means that I can write one of these terms as cosine, another as sine. So I can write this absolute value of C0 as cosine of some angle divided by 2. And here sine of angle divided theta divided by 2. Now it seems illogical to use theta over 2 instead of theta. Seems illogical at this step, but well, let's do it like that. Because this will lead to correct results later. So like people probably first try probably was to write theta, and then it was correct. So this theta changes from 0 to 2 pi, to 180 degrees. Why? Because these are absolute values of this coefficient C0 and C1. So both cosine and sine must be positive. And cosine and sine are positive only when the angle itself is from 0 to 90 degrees. Here I have angle divided over 2, so that means that theta is from 0 to 180 degrees. Okay, so if I am using such notation, so this is the absolute value, but I also have phases here. So these are complex numbers. So I can also have phases. So if I include phases, so this C0, I can write it like some phase factor times the cosine. And C1, I can write as another phase factor times sine. And here in this other phase factor, I write it like this, the same gamma plus something different. Why I use the same gamma? Because when I combine it, I will have here this global phase e to I gamma that I can neglect because I know that it is not physical. So what remains is this expression, which can be, so 0 component is cosine theta over 2. 1 component is this exponential phase factor times sine theta over 2. What are the changes that, what are the limits in which angle change? Theta changes from 0 to pi, as we established, and this phase factor can be arbitrary, so it changes from 0 to 2 pi. And this is exactly the range of angles in a spherical polar coordinate system. Spherical polar coordinate system. We have polar angle theta that changes from 0 to pi. And we have azimuthal angle phi that changes from 0 to 2 pi. Okay, so what this expression gives? It gives that if we have arbitrary qubit state and we neglect this unphysical phase, then for each qubit state, each qubit state can be described by angles in the spherical coordinate system. And that means that for each qubit state, I can put, so I can draw a point on a unit sphere that has the same value of theta angle and phi angle. So like this. So for each qubit state, I can say it corresponds to a unit vector pointed on a unit sphere, which is defined by this angle, theta and phi. So such sphere is called Bloch sphere, and such vectors that correspond to qubit state is called Bloch state. Okay, so this is, I rendered it as illustration of the Bloch spheres. It's like this. So north pole corresponds to state like north pole is when theta is 0. When theta is 0, I have here 1 and 0. So north pole corresponds to state 0. South pole is angle pi, like this. So when angle is pi, I have here 0, here 1. So on this Bloch sphere, here is our basis state 0, here is basis state 1. All other states on this sphere correspond to different superpositions. If we change the value, relative weight of this coefficient C0 and C1, we are changing polar angle. If we change in phase between two components, like from plus to pi and so on, we are moving in azimuthal direction along the sphere. Okay, so this sphere is useful. We will use it next time when we will study what we can do with qubits. So please bring your own Bloch spheres. Yeah, and actually 1 qubit quantum computer is nothing more than a ball, and you can do 1 qubit quantum computation using this mechanical analogy. So Bloch sphere is also very closely related to spin 1/2 particles. So it's not just a mathematical trick. Suppose we have like many electron spins. So many electrons for which spin state we prepared a particular spin state. So we have many of spins in this state. And we will measure, like we have many, so we have ensemble, so we can do classical measurements. So, and we measure this direction, average direction of spin. For such ensemble of electrons. So what we will get as a result? We will get exactly Bloch vector. So this is it has like the direct analogy. So it's not just like we can measure Bloch vector. You create a lot of spins in a particular quantum state, you measure direction of spin or direction of magnetization, and then times -1, you will get Bloch vector. So mathematically, we can formulate it like this. What does it mean that we measure average direction of spin? We measure expectation value of this operator, Pauli operator, sigma x, y, z. Operators, they are, well, when we are talking about spins, they are represented simply by matrices 2 by 2. So we measure these expectation values, or we can, and this gives me like components of this Bloch vector. We can write it nicely in vector form. And this is actually a basis of quantum state tomography for a single qubit, which will be your first lab. So I will be talking more about that during seminars. So for now, let's move on. So this relation, like this measurement of Bloch vector, is actually allows us to determine state of a qubit, completely restores wave function, which is called quantum state tomography. Okay, but that will be covered on the next seminar. So let's consider some special points on the Bloch sphere. So as I already said, 0 and 1 corresponds to north and south poles of this. So all the poles on the equator of the Bloch sphere, they correspond to equal superposition of 0 and 1s. So I have exactly the same like content of 0 and exactly the same content of 1. With photon polarization, that would correspond either to diagonal polarization exactly at 45 degrees or exactly circular polarization, like that. So something that has exactly the same horizontal and vertical components of polarization. What's the difference for different points? It's just the phase relations between 0 and 1 component. And this special points, some of them, they have special notation. So first of all, as you can see, the 0 and 1, they lie on the z-axis. So these two states are often called z-basis states, because this is z-axis. So these are the points on the axis of this are z-basis, because it has actually some deeper relation to basis, but we will consider this later. So, but when we are talking about three-dimensional coordinate system, we have three axes, x, y, z. So we can also consider as a special points that lie on the x-axis. So this is a point that lies at the positive x-axis or negative x-axis. So these states are often denoted as plus and minus. And these are the states that very often used in quantum computing, because like many quantum programs, they start with creating states like plus or minus of different quantum algorithms, like that. And there are states along y-axis or y-basis states of this state that for which phase is plus I or minus I. So these states are useful to remember because many, as I said, many quantum algorithms like use these notations and like introduce the states without further explanation. Have to remember all the states. So all the states are equal superposition of 0 and 1. They differ only by phase that stays here. So all these four states can be written with one formula. State psi, where psi is plus, minus, I or minus I. So this is 1 over square root of 2. 0 plus this psi. For example, if psi is I will have state I, 1 over square root 0 plus I1. You can also remember whether these states lie on Bloch sphere, because if you look this xy plane as a complex plane, real part, imaginary part, that these are plus 1, minus 1, I and minus I. These are 4 complex numbers, and these states are exactly localized at these places. Okay, we will work more with them later. Okay, one more note. So we use and like usually this is used 0 and 1 as basis state. So we wrote arbitrary qubit state as a superposition of the states. Okay, but while z-axis is not different from x-axis or y-axis or any other axis. So instead of 0 and 1, which are point on z-axis, z-basis, we can use any pair of points or any pair of quantum states which are like opposite to each other on a Bloch sphere. And these 2 pair of states will serve as perfectly fine basis with the same properties, the same everything. So, and this is the reason why these 2 points, states, they are called z-basis state. Because this is a basis related to this z-axis. What is x-basis state? This is a point that lie on x-axis, plus and minus, and we can write everything. We can write general qubit general qubit state also as psi, which is some c plus c minus minus. This will be, I can write general qubit state also in this form, because this is just a different basis. So the same as we can choose different direct orientation of coordinate system in 3-dimensional space is just up to us. We can choose different bases for qubits. Sometimes this point of view is very useful. Because some operations you can think of like if you don't, suppose you know how to rotate. Okay, we will consider this on the next lecture. Okay, the last topic for today's lecture is qubit measurement. So if we want to get information from quantum world to ours, we need to measure qubit. We need to measure qubits, probably more than one. So there are important difference of quantum measurement compared to classical. The measurements are probabilistic. When we don't measure quantum systems, there is nothing probabilistic or random about dynamics of quantum system. So when this quantum system evolves by itself without us looking at it, there is absolutely no randomness there. There's absolutely so that everything is determined. So randomness, the only source of quantum randomness is when we measure it, when we measure quantum system. Why that happens, actually, we don't know. This is one of open problems in quantum physics, the measurement problem. It just happens. Okay, so they are measurement. And measurement change the state of the quantum system. Okay. So, how measurement is done on an example of superconducting qubits. So here is like a schematic view of this measurement process. So here we have qubit, which can have state 0 or 1. And this qubit is connected to a resonator, which is called the readout resonator. The resonance frequency of this resonator is not the same as the frequency between 2 qubit levels. So whatever signal we send into this resonator will not influence whether we have 0 or 1. So this signal is not resonant for qubit. But what happens? Resonant frequency of this resonator, it changes depending on whether we have qubit in state 0 or qubit in state 1. So physical process through which it changes is called like dispersive shift. This is something that we will study at the end of the course. But here is the mechanism like that. So resonant frequency of this circuit changes depending on whether qubit is in state 0 or 1. Then we send probe signal into this resonator, and basically we measure phase shift of reflected signal and determine whether we have resonance frequency corresponding to state 0 or resonance frequency corresponding to state 1. So this is how readout is done. for superconducting qubits. For other qubits, well, it's done differently. As the result of this readout, we will get result, whether we will get result 0, that okay, qubit is in 0, or we will get result 1, so qubit is in state 1. Now, back to your question. What happens if qubit is in superposition of state? What happens in this case? We will get randomly. We will never get superposition. So this is a property of quantum measurement. You do this measurement, and it doesn't depend on particular way how we measure the system. So you can invent different way. Well, like you will never get an answer that qubit is in superposition. So with this probability, so we have qubit in such superposition state, C0 and C1. Then with probability C0 squared, the outcome will be 0. With probability C1 squared, the outcome will be 1. We will never get superposition as an answer. So here is the source of randomness. So we created a superposition. We can create very well-defined superposition. We know what the state is. We measure it, and here we get random answer.
How do you know?
What?
Your state is in the superposition state.
Yes.
How do you know?
How do I know that?
If you cannot measure it.
That's absolutely excellent question. Welcome to my March 24th lecture. That's actually the question that I will ask all of you, like my first question. How do you know that qubit is in superposition before you measure it? Absolutely excellent, and we can do it. We can do it, but let's so you have very right way of thinking. So as I say, so this is very deep question. How do you know like that something exists like before you measure it? Like you measure it, like you destroy this thing, or like we measure superposition and we say so that measurement destroys superposition because we have 0 and 1. How do we know that superposition existed before we measured, right? Absolutely excellent question. For me, it took much longer to ask this question myself. So, but this will be covered later. Like you can think yourself, what would you do? How would you distinguish? It is possible to make set of experiments yourself. Okay, but we know we can do experiments that will show, or you will do experiments that will prove that whatever equations we write, no matter how strange they are, they represent reality. And whatever we think about reality, everything is wrong. Okay, so this is what we get. So here we have answer answer is probabilistic, and most important that qubit collapses to this state. So we had qubit in such superposition. We measure it, and we get answer 0. And also, what is also important, that qubit collapses to this state. So we measure qubit with some state, we get answer 0. After the measurement, qubit will be in this post-measurement state of qubit collapses from superposition to 0. That means that every qubit can be measured only once. Because we may have some superposition. We measure it and we get some outcome, 0 or 1. Or we can measure it differently. We get some, but we get some answer. And qubit collapses to the state. And then we know what the state of the qubit is. So measuring second time does make any sense. So once we measure qubit, we measure it once. Everything, like all the information that existed in this superposition vanishes. Well, this information is somehow, it determines probabilities of our outcome, 0 or 1, of course. But, well, we measure it, we get 0 or 1, and everything else, well, is removed. Okay, so every qubit can be measured only once. So from measuring of a qubit, we can get only 1 bit of information. And this information is probabilistic, but, well, we will get it. Okay, so this is a simple rule that, well, if we measure qubit in this state, then probability of getting answer 0 is C0 squared, and probability of answer 1 is C1 squared. we can rewrite these general rules in a different form. So what is C0 squared? How I can define it? Well, C0 is this coefficient. I can write this C0. So if we have a vector, and we need to take only one component of this vector, how do we do it? We take scalar product. So this C0 can be found simply as 0 scalar product with state psi. And C0 squared is just this square, this scalar product squared. Similarly, for probability of observing state 1, it's just the scalar okay, here it should be 1. So it should be just scalar product of 1 with psi and absolute value squared. Okay, and this represents a general rule. Like if we measure a quantum system, qubit or even some more complicated quantum system, doesn't matter. And we measure, we ask a question whether the system is in some state A. So this may be 0, 1. Well, probability that the answer will be yes is just the scalar product of this state, or of the state in which we have system, and the state in which we want to observe it. Okay, so, and this is Born rule, and this is like the main rule of quantum measurement. So whatever type of measurement you have, you can use this rule and predict the outcome. Okay, briefly about some other important topics which will be important for your first lab. So here, like when we ask question, is qubit 0 and 1, we force qubit to choose one of these two states, 0 and 1. So we perform measurement in Z basis. But Z-axis is not special from any other axis. So as likely, we can also ask question whether qubit is in state plus or minus. So this will be measurement in X basis. How to find probability of that? Well, that qubit is in state plus. Well, this is general rule. We have state of the qubit. If I want to find probability for such X basis measurement, probability that qubit will be in state plus, well, here I should use state plus. General rule. What happens after this measurement of a qubit? Well, qubit collapses to corresponding state. If I measure qubit in X basis, and I obtain results that it is in state plus, well, after measurement, I can be sure that qubit is in state plus. Okay, so we will consider this example probably on seminars. Okay, so we can choose different axes for measurement. Now, quantum computers in which you will be working, they can measure like physically, they can measure only in Z-axis. Or only in Z basis. But there are tricks how we can simulate measurements in different bases and actually measure any projection, or like projection on any axis we want. One important question here, very short, in this distinguishability of quantum states. We can ask question whether is qubit in state 0 or 1, so measurement in the axis. We can ask question whether is qubit in state plus or minus, so measurement along x-axis. But we cannot design a measurement that will determine whether qubit in state 0 or state plus. So we choose an axis, and then we can perform a measurement on any axis. But these 2 points, they are not on the same axis. So what that means that these 2 states are not orthogonal to each other. So they are not orthogonal. Scalar product of 0 and plus is not 0. It's 1 over square root of 2. So these states are not orthogonal. And that means that we cannot design a measurement that will tell whether qubit is here or here. So this so such state, like if we have, such state cannot be distinguished by quantum measurement. Of course, when we are saying about this distinguishability, if we have a single qubit, say, I prepare a qubit in state 0 or state plus, and give qubit to you. You have just one qubit. You cannot determine with certainty whether it's 0 or plus. You can do some probabilistic, you can make some measurement and give me answer which will be correct 75% of time, but not 100%. If I give you qubit in state 0 or 1, but you don't know which state, but it's 0 or 1, not superposition, 0 or 1, you can perform measurement in the axis and you can tell from one measurement whether this is 0 and 1. For non-orthogonal states, this is not possible. And there are some quantum communication protocols that take their security from this fact, that if we send one qubit in non-orthogonal encoding, then whoever listens to your communication cannot distinguish between these two states. But what we can do, we can distinguish it statistically. If we have like thousands of qubits prepared either in one state or another, we can perform thousands of measurements, and then we can say with very high probability whether it was state 0 or plus. So all these quantum communications, they have to use like single qubits. They work on single qubits, not on ensembles of qubits, because otherwise we will use all security. Okay, that will be all for today. Thank you for your attention. Do you have any questions? Okay, then, okay.
Question about this global phase, this is always the same. This is the fact for any, like not only the single magnon, it's the same for single photon, single...
Absolutely,
like
absolutely, yes.
One wave function, the global phase of this wave function is...
Yes, yes. It's not just for single, for any Fock state. Like if you have state with a definite number of quanta, any Fock state, it doesn't have phase. You need to have superposition.
But how can we imagine, like if one imagines like a photon as some energy of an electromagnetic field, and it has these two components, the magnetic field and the electric field.
And these two components, they are completely random. So you say you have one component, like you measure, so it's an oscillating field, so you would expect the phase would change in time. So you can kind of say predict that at this moment of time you should have a minimum of electric field. And you do measurements and you see that you can get like absolutely any value of electric field. For one component and for another, well, you need to of course, to have many copies of the same state to make measurement, because you measure, you change the state. But you measure many copies of the same state, you get like, you see, yes, there is field, but it can be positive, negative, so it can have any value. So like on this, say if we are talking about magnons, so magnons precess. So classically, if we have magnons, we have magnetization, it moves in a cycle. So it has precession. And so you excited magnet at a certain, like you excited classical spin wave, and then like half period later, you measure X and Y components, you will get something here, right? Now you excite single magnon. What you will get? You will get like results all over the place. That's actually something that needs to be done experimentally. But this is what predicted by theory, that you will not get any phase at all. No distinction between not a particular place on the diagram. It will be centrally symmetric, which immediately means that you don't have any phase. Any other questions? Okay, then I will see you next Tuesday. We have both lecture and seminar here, right?